Waves can be broken down into two main types, mechanical waves and electromagnetic waves. Mechanical, we can think of mechanics or physical. They require a medium to travel through. A medium could be air, it could be water, it could be steel. In other words, some sort of physical material. Electromagnetic waves, they can travel through certain types of mediums such as air or water. It depends on whether they're opaque or not to that particular frequency. But they can travel through a vacuum. Can travel in a vacuum. Now, you should know this idea because in space we have a vacuum between us and the sun, and we can see the sun. And that's because light waves are electromagnetic and they can travel from the sun to the earth. However, sound cannot travel in space because sound needs a medium. If a spaceship in a movie blows up and you can hear the explosion, that's actually not true. You wouldn't be able to hear the sound waves. Sound waves are mechanical and they need a medium like air. So longitudinal waves, they are mechanical. Now, we already said the definition of a mechanical wave is that they travel parallel to the propagation. What I did was I wrote longitudinal this way with the L's that are parallel to each other to help you to remember that that's the type of wave that longitudinal are. So it's moving this way and it's propagating parallel to that. So in this case, the speed depends on the medium. In other words, it depends on what it's traveling through. So the main speed that you're going to end up using is the one that we looked at before, the speed of sound. But notice it says in air at standard temperature and pressure. So this number is usually what you're going to use for sound and air, but they might give you a different number if the temperature or pressure are different. What you do need to know on your own from this is that as density goes up, speed goes up. And I think that makes sense because you know that sound travels faster through water than it does through air. So the best example of a longitudinal wave is sound. And what are we talking about here? Well, in air, sound goes slow. In wood, it goes a little faster. And in steel, it goes really fast. That's because these are getting more dense, and as density goes up, speed goes up for sound. You just have to memorize that. But what about temperature? So speed also depends on pressure and temperature. Now, the main one that you need to know about is temperature, because pressure is basically related to density. But let's talk about the thing that's most important, which is temperature. You need to know that as temperature goes up, speed goes up. So finally, we did this in the electricity unit, but I'm just going to go over the concept one more time, because these questions end up getting asked in the waves unit. If you have a person standing away from a lightning bolt, the lightning bolt produces light and it produces sound. So the light is an electromagnetic wave, that's transverse, and that travels at 3 × 10⁸ meters per second. The sound wave is longitudinal, and if it's at STP, that travels at 331 meters per second. Both of the numbers, the speed of light in a vacuum, which is basically the same as air, and the speed of sound are on the reference table. And you can solve these without V = F lambda. You can just do V = d/t if they tell you how far the person is from the lightning strike. Transverse waves, they vibrate perpendicular to the propagation. So I like to write the T like this to put a little perpendicular sign in there to remind me that transverse waves, while they propagate this way, they could also propagate that way, the vibration is perpendicular to those two directions. And all electromagnetic waves are transverse. So how do you get an electromagnetic wave? Well, they come from vibrating charges. Typically, most electromagnetic waves are made from electrons that are moving up and down. So that moving electric field produces an oscillating electric field that can travel through a vacuum. But this oscillating field, if you remember this from the electricity unit, the changing electric field produces a magnetic field that is perpendicular to the electric field. And that's why it's called electromagnetic, because it's an oscillating electric field and an oscillating magnetic field. This could also be a proton. But typically when we're making them ourselves, electrons are free to move in wires, so we use electrons. Now, the electromagnetic waves have different names depending on their frequency and their wavelength. At the low end of the spectrum, we have radio waves. So these are going to be low frequency, and they're going to have a long wavelength. As we go further along, we get to microwaves, then infrared, then the visible spectrum, which we're starting with red here, infrared, so then becomes red, orange, yellow, green, blue, violet, then ultraviolet, X-rays, and gamma. And when we're down on this side of the spectrum, we're talking about a very high frequency and a very short wavelength. So if we were to draw this out, we would have waves that get shorter and shorter and shorter and shorter frequency, all the way to here. Don't confuse frequency with speed. All of these travel at the speed of light. C is celeitros, which is the Latin for the speed of light in a vacuum, and that's 3 × 10⁸ meters per second. So no matter which of these you're talking about, they all travel the same speed. Radio waves include your cell phone waves. Microwaves can be generated from a microwave oven. Infrared is heat. This is the visible spectrum. This is only a very small sliver of the entire electromagnetic spectrum, but I drew it large so you could see all the different colors. Then ultraviolet is what gives you a tan. X-rays are obviously can help you to see your bones, to see if you have a broken bone. And then gamma rays are the most energetic, and these actually are cancer causing. So we have these different types of waves, and the reference table actually lays these out for you. And not only, they have them in the reverse order here. Not only do they give you the wavelengths and the frequencies, but they give you the breakdown of the exact frequency ranges for the colors. Now, remember that a color isn't a single frequency. It's a range. It's a range between two different frequencies. So if we have a number in between here, then we're talking about violet. So another thing that you need to know about the speed of light is that the speed of light, and when I say speed of light, we're talking about the speed of all electromagnetic waves. They really shouldn't call it speed of light. They should call it speed of electromagnetic waves. But it's up to you to know that speed of light means electromagnetic waves. The speed of light is affected by the medium. So it will slow down if it's going in a material other than a vacuum. Now, air has such a low index of refraction that it travels basically the same speed. Light goes only a little tiny bit slower in air. And there's a formula for figuring out how fast it's going, and that is n = c/v. N is called the index of refraction. And you can use this formula to figure out, using 3 times 10 to the 8th meters per second, how fast the light will travel in this material with this index of refraction. So there's a chart of all of the different indices of refraction. Notice that this is only true for a specific frequency, which happens to be yellow light. So air, you can see, is 1, and in reality it's 1.005, I think. So it's a little bit higher. So light goes a little bit slower in air than it does in a vacuum. And then we have different materials that light can travel through. And as it travels through these different materials, it will slow down depending on the number. The larger the number, the slower light will travel. One more thing that you have to be careful about is that radio are not the same as sound. Okay? Radio waves and sound waves are not the same. Radio is what travels to a radio to the antenna. Sound waves are what comes out of the speakers. Radio waves are electromagnetic and travel at the speed of light. Sound waves are longitudinal, they're mechanical, and they travel at the speed of sound.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.